Today I'm going to talk about Quaternion matrices. Outline: we will go over the definition of quaternions, some properties of matrices over the quaternions, and at last, an algorithm of finding eigenvalues and eigenvectors of quaternion matrices. First of all, what is quaternion? Concisely speaking, it is a four-dimensional associative algebra over the real numbers, with an order basis denoted by 1, I, j, and k, and the multiplication table defined as follows. In other words, the quaternions can be thought of as a four-dimensional vector space over the real numbers, but inside this vector space, not only do we have a addition, scalar multiplication, but also we are able to multiply any two vectors by using the multiplication defined for basis elements together with the linear expansion. Moreover, the multiplication of elements is compatible with the scalar multiplication, which means that scalars can go through elements in the product. To put this simple, we can imagine when we first encounter the complex numbers. We were able to do any computation just by using the fact that I times I is -1. So the same thing is true here for the quaternions. Just like in the complex case where we have the real parts and the imaginary parts, so that we can define the conjugate of a complex number by flipping the sign of its imaginary part. So can we here for the quaternions. The sum of x1i, x2j, s2k here is called the imaginary part of the quaternion x. And we define the conjugate by flipping the sign of I, j, and k coordinates. Since a quaternion is a four-dimensional vector over R4, we can use the Euclidean norm to define the quaternion norm. So for any non-zero quaternion x, we can show that it is invertible by direct computation, and it can also be expressed in terms of the conjugate and norm, which is the same as in the complex case. Next, we give the definition for two quaternions being similar. It is easy to see that this is an equivalent relation. The following lemma tells us how to find a good representative for each equivalent class of the quaternions. It says that any quaternion is similar to a unique complex number whose imaginary part is positive. The proof is just a direct computation. Therefore, for any two quaternions, we can use this lemma to transfer all the weights from the j-k coordinates solely onto the I coordinate. And then after we do that, we don't change the equivalent class. So we can think of the imaginary part of a quaternion as a three-dimensional vector and have the following theorem interpreted as follows. It says two quaternions are equivalent if and only if they have the same real parts and their imaginary vectors also have the same norm. And this unique complex representative of each equivalent class is called the principal number. Because quaternions are non-commutative, it's helpful to think of them as ordered pairs of complex numbers. For any given quaternion, we can factor out the j from the third and fourth coordinate so that we can see that each quaternion has a unique expression as an ordered pair of complex numbers. And this is called the symplectic form of a quaternion. Similarly, for any given quaternion matrix A, we can decompose each of its entries into the symplectic form so that the quaternion matrix A can be uniquely expressed as ordered pair of complex matrices. More importantly, by using such an expression, we can define an injective map from the set of all n by n quaternion matrices to the set of all 2n by 2n complex matrices. The resulting complex matrix is called the complex adjoint matrix of A, which is denoted by chi of A. You may have seen a similar definition in representation theory, which says quaternions can also be expressed in terms of 2 by 2 complex matrices. If we think of the quaternions as 1 by 1 quaternion matrices, we can see that these two definitions are actually compatible. Next, we can check that the injective map we just defined, chi, it actually preserves matrix multiplication. And also, it's not difficult to observe that chi also preserves addition and scalar multiplication. Therefore, it is an algebra homomorphism. The following theorem is free if we think of it from the abstract perspective. It says the algebra homomorphism chi maps the identity to the identity, and it takes the inverse to the corresponding inverse. Now we can answer this question. We know for complex matrices A and B that AB is the identity implies that BA is also the identity. But how about the quaternion matrices? If AB is the identity, then we can apply chi on both sides to have that chi of A times chi of B, it's the identity. Since chi of A and chi of B are both complex matrices, we can reverse the order they multiply so that chi of B times chi of A, it's also the identity. At last, we use chi inverse to pull back to deduce that BA is the identity. Now, we have the following theorem which gives some equivalent statements for the invertible quaternion matrices. A quaternion matrix A is invertible if and only if AX equal to 0 has a unique solution if and only if chi of A is invertible. From 1 to 2 is trivial because you can multiply A inverse on the left side. And from 2 to 3, we start with the equation AX equal to 0 and apply chi on both sides. By the assumption, the vector x1, x2 can only be 0, which implies that chi of A is invertible. From 3 to 1, suppose chi of A is invertible, so there exists a 2n by 2n complex matrix which is partitioned conformally as chi of A. We can observe that the equality still holds even if we replace B3 and B4 with negative B2 conjugate and B1 conjugate, because the equation determined by the blue circles here is actually equivalent to the one determined by the green circles. Since non-zero quaternions are divisible, we can actually have more equivalent statements. For example, an invertible quaternion matrix can be reduced to the identity by elementary row operations. Since performing elementary row operations are equivalent to multiplying the corresponding elementary matrices on the left side of A, we can see that both A and A inverse can be written as a product of elementary matrices. And if we multiply this product by on the right side, we can recover the corresponding column operations. Therefore, we can see that A is invertible if and only if the reduced row echelon form of A is the identity. If and only if the reduced column echelon form of A is the identity. And next, let's turn our attention to eigenvalues and eigenvectors. Since quaternions are non-commutative, we need to distinguish left eigenvalues from right eigenvalues. In the definition below, an eigenvalue is a left eigenvalue if it appears on the left side of the vector, and similarly, it is a right eigenvalue if it is multiplied on the right side. An example here shows that J is a left eigenvalue of the matrix A. But if we put J on the right side, the equality does not hold. So we see that a left eigenvalue is usually not a right eigenvalue, and vice versa. Now the following theorem says that if lambda is a right eigenvalue of the quaternion matrix A, then so it's its representative or its principal number. We know that any quaternion is similar to its principal number, which can be expressed as P inverse lambda P. So we can just rewrite the equality to deduce that P inverse lambda P is also a right eigenvalue of A. And from this lemma, we can see that a quaternion matrix might have infinitely many eigenvalues, since each equivalent class may contain infinitely many elements. And the following notion tells us how to convert a quaternion matrix into a complex one by using the symplectic expression. If we look closely, we see that the complex vector we got here by unfolding the quaternion vector is actually the first column of chi of A. Next, for any non-zero to n-dimensional complex vector, we define its companion vector by reversing the order of v1, v2, as well as changing v2 to its negative conjugate. If we place a pair of companion vectors together, we can see that they actually recover the complex adjoint matrix. So the lemma here says a pair of companion vectors are always linearly independent. The proof is straightforward by direct computation. Suppose one is a multiple of the other, then we can use substitution to deduce a contradiction. Now we have a super useful theorem. Let A be any quaternion matrix and chi of A its corresponding complex adjoint matrix. The theorem says that the quaternion matrix A has literally the same complex eigenvalues as its complex adjoint matrix. If the pair lambda comma w is an eigenpair of chi of A, then so is the pair consisting the conjugate of lambda and the companion vector of w. Basically, it says that if you have lambda as your eigenvalue, then you also get its conjugate for free. For the proof, we suppose that V is an eigenvector of A associated with the right eigenvalue lambda. Then we can apply both chi on both sides to have the equation 4. And if we split this matrix in half, we can deduce the following two equations. Moreover, we can observe that equation 5 and equation 6 are equivalent. And since chi is injective, we can see that these 3, 4, 5, and 6, they're all equivalent. So we see that A and chi of A have the same complex eigenvalues. And from 5 and 6, we can also see that two complex eigenvectors of chi of A associated with the conjugate pair of eigenvalues respectively is companion to each other. Therefore, we can see that each complex eigenvalue of the Quaternion matrix A is one-to-one corresponding to a pair of conjugate eigenvalues of chi of A. Moreover, since each pair of the companion vectors are linearly independent, all real eigenvalues of chi of A have multiplicity even number times, and all non-real eigenvalues of chi of A appear in conjugate pairs. And therefore, we can see the next two theorems here. For a matrix like this, we know exactly what its eigenvalues are like. And we also know that any n by n quaternion matrix has exactly n right complex eigenvalues whose imaginary parts are non-negative. They are those principal numbers or representatives of the equivalent classes. The next theorem tells us that a quaternion matrix is diagonalizable if and only if its complex adjoint is diagonalizable. The proof: assume that the quaternion matrix A is diagonalizable, then there exists a invertible quaternion matrix Q which puts A into the diagonal form. Now, we don't rush to apply chi of A on both sides because these lambdas now they are still quaternion numbers, which will make the image very messy. Instead, we want to find their principal numbers to construct another transition matrix P. Now, we use the matrix P to reduce the expression on the right side so that it is a complex diagonal matrix. Then we can apply chi on both sides, and we can see that the output is also a diagonal matrix. Therefore, chi of A is diagonalizable. Conversely, suppose that chi of A is diagonalizable. By our previous theorems, we know that its spectrum is like consisting those conjugate pairs. And now, not only do we want to find any random linearly independent eigenvectors, but also we want them to appear in pairs of companion vectors. Also, we would put them in this special order in order to construct our complex transition matrix so that we can recover the quaternion transition matrix later on. Since P diagonalizes chi of A and P is in the image of chi, we can pull back to recover our quaternion matrix as desired. And therefore, we have that A is diagonalizable. There is a quick corollary here. If an n by n complex matrix is not diagonalizable over the complex numbers, then one may ask, would it be possible for it to be diagonalizable over the quaternions? And the answer is no, because the complex adjoint of A is a 2n by 2n block diagonal complex matrix consisting A and its conjugate. So it's not diagonalizable because one of its blocks, which is A, is not. Now let's take a look at an example I constructed. Let A be this 2 by 2 quaternion matrix. To find all of its quaternion eigenvalues, we firstly write out its complex adjoint matrix and compute its characteristic polynomial. We see that it has two real roots and a conjugate pair of complex roots. Now, for this pair lambda 1 equal to lambda 2 equal to 1, we find a pair of companion vectors which will be linearly independent automatically. And for the other pair, we do the same thing, and after that we put these eigenvectors in this order to construct our transition matrix P, which diagonalizes chi of A. And now we cover the quaternion vectors from each pair of the companion vectors and use them to construct our quaternion transition matrix Q. And we see that A has been diagonalized. And now we can write out its right spectrum by taking the union of the equivalent classes of its complex eigenvalues. Now let's try to find the left eigenvalues of A. This time we place lambda on the left side of the vector V and apply chi on both sides. And we split, just cut this in half, and we can deduce the following equation, 10 and 11. But now we can see that neither lambda 1 nor lambda 2 is an eigenvalue of chi of A, because the previous way they multiply the vectors has been twisted. We have no way but just to continue the algebra to see that finding a left eigenvalue of A is equivalent to finding a pair of complex numbers lambda 1 and lambda 2, such that this determinant is equal to 0. However, methods of finding such a pair in general are still unknown. But what we do know is that such a pair always exists, and I'm sure we can find it someday. So that's it for my presentation today, and thank you so much.